Greetings, everyone. In this lesson, we're going to talk about verifying trigonometric identities. But before we talk about verifying trigonometric identities, let's actually talk about what an identity is. An identity is an equation that's true for all values of the variable for which the equations or the expressions are defined. So let's think back to Algebra 2 for a minute and think about solving an equation like this one I have up here in the upper right-hand corner. Well, if I was going to solve this equation, I'd probably combine like terms and I would get 3x minus 2 equals 3x minus 2. And some of you might recognize that the left-hand side and the right-hand side here are the same, so this will always be true. This equation will always be true for any value of x. That's what we mean by an identity, that the expression will always be true no matter what value x is. And we've actually already worked with some identities in trig. We have reciprocal identities, the fact that cosecant is a reciprocal of sine, and sine is a reciprocal of cosecant. That's one of the reciprocal identities. We also know cosine and secant are reciprocals, and tangent and cotangent are reciprocals. So those are reciprocal identities that we've already worked with. We also have some other identities that we've worked with, the quotient identities. We know that tangent is defined as the ratio of sine to cosine, and cotangent is the ratio of cosine to sine. And then we have some new identities here called the Pythagorean identities. And if this kind of looks like a squared plus b squared equals c squared to you, then you're on the right track, because that's where this Pythagorean identity comes from. It comes from the fact that if we talk about a point on the unit circle, talk about sweeping out this angle in standard position, and we talk about this point on the unit circle, we know that the point has an x-coordinate of cosine and a y-coordinate of sine, and we know that the hypotenuse of this right triangle will be 1. So if we think about the Pythagorean theorem and substitute the numbers in, we'd have sine squared, that's our y value squared, plus cosine squared equals 1. So this is like our a squared plus b squared equals c squared, except we took the y-coordinate squared plus the x-coordinate squared equals 1 squared. So that's our first Pythagorean identity. But how do we get these other two Pythagorean identities? Well, let's say that I wanted to divide both sides of this equation by cosine. So I'm going to divide each part here by cosine. I should say cosine squared. So I'm dividing each term by cosine squared of the angle. And notice here we have sine squared over cosine squared. Well, sine over cosine is tangent. An expression divided by itself, that's just going to simplify to 1. And 1 over cosine, we know that cosine is a reciprocal of secant. So simplifying this expression here, after I divided by cosine squared, gives me our second Pythagorean identity. Well, how do we get our third Pythagorean identity? How do we get the identity that's over here on the right? Well, instead of dividing by cosine, let's actually divide everything by sine squared of x, and see what happens. Well, if I divide everything by sine squared of x, notice that my first term is sine squared of x over sine squared of x, which is 1. And then cosine divided by sine would be cotangent. And then 1 over sine, well, the reciprocal of sine is cosecant. So those are our three Pythagorean identities, and they're going to become very helpful or come in handy when we're working with simplifying other expressions involving trig. So let's take a look at two such expressions. So here we're going to try to simplify this expression by first changing everything into sines and cosines. And you might say, well, we already have everything in terms of sine and cosine. Well, almost. We need to change cotangent to its version of sine and cosine. Cotangent, remember, is cosine over sine. So we'll have cosine of x over sine of x times cosine of x plus sine of x. And what I'm going to do right now is I'm going to rewrite this part right here, think of this as being over 1, and multiply the numerators together. So I'd have cosine of x times cosine of x, or cosine squared of x. And in my denominator, I'd have sine of x. Well, in order to combine these two fractions now, I need to have a common denominator. And so my common denominator is going to be sine of x. So I'm going to put the denominator of sine of x here, but if I multiply the denominator here by sine of x, I also have to multiply the numerator by sine of x. Right? And you might think, wait a minute, what did she do there? Basically, it's just like if I wanted to convert this fraction to be in terms of fourths, I would multiply, or let's say in terms of a common denominator of 10, I'd multiply the denominator by 5 and the numerator by 5. I just multiplied by a form of 1, right? And we have an equivalent fraction of 5/10. That's essentially what I'm doing here. I'm getting an equivalent fraction. So let me simplify this here. I'd have cosine squared of x plus, now sine times sine gives me sine squared of x, all over my common denominator of sine of x. And we know already that sine squared plus cosine squared is 1. So we have 1 over sine of x. But wait a minute, that's one of those reciprocals. Which one is that? Oh, it's cosecant of x. So this all simplifies to cosecant of x. Let's take a look at another example. In this example, we have cosine squared here. And if you remember, we said sine squared plus cosine squared equaled 1. That was one of our Pythagorean identities. Well, I really want just cosine squared here, so I'm going to solve this for cosine squared. And I know cosine squared is 1 minus sine squared. So now I can actually substitute this expression in place of cosine squared here. So let's do that. When we do that, we have 1 minus, and in the numerator 1 minus sine squared of x. And in the denominator 1 plus sine of x. So now you might be thinking, wait, this is a perfect square and this is a perfect square. That's a difference of perfect squares. So let's factor that. We'd have 1 minus sine of x and then 1 plus sine of x. All over our denominator of 1 plus sine of x. And then, oh wait, these cancel. Well, that's good. Let's see if that helps us out in terms of simplifying this. I'd have 1 minus sine of x. That's in parentheses here. And so then I need to distribute the negative. And when I distribute the negative, I have 1 minus 1. And then, let's see, negative times negative. That would give me a positive sine of x. And, well, let's see. This just becomes sine of x. So even though this expression looked really, really complicated, this entire expression here is equivalent to sine of x. So we'll be taking a look at more of these ideas in class tomorrow.